Okay, the goal of this problem is to see what these look like if we try to get forces involved and solve the problems algebraically instead of always having numbers. So in this case, I want you to imagine we have a cylinder with some gas in it. It's basically, just like this situation right here. So we've got a piston in there. This is free to move up and down. And obviously, if I seal this a little bit by sealing the hole, we notice that the mass doesn't fall down, whereas if I let off the hole, we see it falls down. So you've got some gas trapped in here, and we seal the leaks, and as a result, you have some trapped air volume right here below the piston. Whoa, the piston is this metal cylinder here. There's the air volume that we're talking about, and we're going to assume we have hydrogen in there for some reason at some temperature, capital T. So our knowns in this problem, and we know the gauge pressure. And we know the outside pressure. So this is what we know. Our goal is to figure out the piston mass. Think. If you want to pause the video and try to do it yourself, that's great. This is on page 77 of the workbook. Volume 3, if you want to look at it. Pause the video, try to do it yourself. I'm going to proceed in 3, 2, 1. All right. How can I get mass involved? Free body diagram. I'm going to draw the free body diagram of the piston. Why don't you pause the video, just take a quick shot at it, and then unpause the video. By trying, you'll remember the right answer more. 3, 2, 1, here we go. FBD of piston. Okay, so here's the piston. I'll just do a pure side view. Well, I know there's mg. Right, that's the weight that was causing the piston to fall down. What's the force that's holding it up? Well, there's pressure here. And so how does pressure relate to force? I know that pressure inside is equal to force over area. Or notice the force from the inside that's pointing upwards should be pressure inside times area. And then just, okay, let's leave it at that. So now, is that everything? No. There's also atmospheric pressure pushing down on it, right? So, all right, so there's got to be some. Similarly, the downwards force would be P0 times area. So this is one of the things I wanted to just give you the tip here. If you're talking about forces and pressures, we can convert them back and forth using the area. If you have the force and you want the pressure, you divide by the area. If you have the pressure and you want the force, you multiply by area. That's it. So then maybe just to make this look a little bit cleaner, okay, there we go. And I'm going to need some room. Now think, is this thing accelerating? Well, that's supposed to be this scenario here, where we lift this up, we trap the gas by sealing the valve, and we see it's not accelerating. All right? So in this case, the acceleration is 0. That means the ups equal the downs. So we're looking for mass. Don't forget, keep your eye on the prize. Rearrange that ratio. Move this to the other side. I'm going to factor out the area. What is this term right here? P inside minus atmospheric. That is P gauge. So this is why we often use gauge pressure. If you're trying to figure out forces, the gauge pressure, right, accounts for the pressures on both sides not being equal. The pressure difference, or the gauge pressure, is what relates directly to the net force from the atmospheric conditions on both sides. So let's just say that's P gauge times area over G. Now in this case, the gauge pressure we're told in this problem is 2P naught. All right, so the gauge pressure is 2P naught. And I got to check this solution here, or the question really quick. Want to make sure I'm doing the right one. I have it wrong here. All right, so we'll come back to that. Sorry about that. I just saw this and I'm like, wait a minute, that didn't make sense. Okay, so at this point, we know everything except for the area, but we should be able to figure that out from the cylinder diameter. The area, the piston area is just that of a, right, it's a circle, right? Oh, you can't see that at all, right? No, whatever. There you go. You can see it's a circle there. Maybe if I stand in front, oh, whatever, bad shirt today. Okay, area is pi r squared. Is pi times diameter over 2 quantity squared. It's pi diameter squared over 4. We can plug that into here and we get gauge pressure, which is 2P naught times the area. That's pi d squared over 4. And then here, I guess we could clean this up. P naught d squared pi over 2g. All right. I'm just going to check, make sure that's the same answer I got before. Looks like it is. Okay, good. So that was part A. All right, and hopefully that makes sense. This is kind of the part I wanted to focus on here, how to get the FBD, get the pressures involved, forces, etc. So that was kind of the new bit. All right, and then let's check. What is number of moles? How do I get that? If I want to get number of moles, let's use the ideal gas law. Think, what pressure do I need to use? Gauge pressure, ambient pressure outside the tank, or the absolute pressure inside? We need to use the absolute pressure inside. So here, why don't we take a minute and figure out what the actual pressure is inside? We know the difference between inside and outside is 2, so this is probably 3P naught. But let's go ahead and work that out. We know P gauge equals P in minus P naught. So moving that over, we should see that P inside is the pressure that we want to use for P equals nRT is 3P naught. All right, so then here, 3P naught, what's the volume of the cylinder? Area of the base times the height. T was a given in the problem. You you can rearrange this and get the answer. If you actually had numbers to plug in, then you'd want to be very careful with the units. This R uses joules, so if you were plugging in units, we'd probably use meters, not centimeters or millimeters, and we'd use pascals. 1.01 times, 1.013 times 10 to the fifth pascals. All right, so now, let's say you add grains of sand until the piston doubles, piston mass doubles. So you're just basically, you've got this situation, you're like, oh, I'm just gonna gradually add some mass here until the piston doubles, all right? Now, when this happens, what would be the new gauge pressure? So here's where it gets a little bit sneaky. If we double the mass, notice the gauge pressure doubles because mass is directly correlated to gauge pressure, not absolute pressure. So the new gauge pressure would be 4 P naught. Whereas if I had said, what is the new pressure? Would be 5 P naught. And so this is one of the annoying things about gauge pressure. If you double the gauge pressure, we don't double the pressure. We were at 3 P naught, but doubling the gauge pressure actually only raises this to 5 P naught. So that's another thing I wanted to focus on. We have the free body diagrams, but also watch out for gauge pressure. When you're going back and forth, when you use PV equals nRT, you want to make sure you're using absolute pressure, the pressure inside. And just because you double the gauge pressure does not mean you double the pressure inside. That's a common thing, especially in a chemistry class, you'll get dinged on. All right, so watch out for that. And then lastly, based solely on the ideal gas law, can we determine the new temperature or new volume and temperature? So think about this. You've got this situation here, like this. And now what we're going to do is we're going to add some mass to it. All right, and so when I do that, that's not changing it very much, but it does change a little bit. All right, and so the question is, can we figure out the new volume and temperature when we do that? Assuming we only know the ideal gas law. I've kind of run out of room here, so I'm going to erase a little bit. I'm going to use this area right here. All right, and what do we know? We know P initial, how would I call it P1 for the starting case, was 3 P naught. We know P in the final case was 5 P naught. We know the container is sealed. You didn't see any air leaking out. So we're assuming the number of moles in the first case is equal to the number of moles in the second case. A classic thing to do with PV equals nRT problems or ideal gas law problems is to set up a ratio. P1 V1 equals N1 R T1, and then we'll do P2 V2 all over N2 R T2. R doesn't need a subscript because that's a constant. So we're essentially taking a ratio to compare these two. This works great in many, many cases. Let's see if we can use it here. Well, I know the number of moles is the same before and after. I know that the constant drops out, and then in this case, I know that the ratio here would be this one over this one gives me 3 over 5. But now what do we see? Well, we know the initial volume. That was pi diameter squared h over 4. The final volume would be pi diameter squared 4 over some new height. The problem is we don't know the new height. We know the initial temperature was T, but we don't know the final temperature, T prime. We have two unknowns with one equation. We do not have enough information to figure this out using the ideal gas equation alone. Later on, we're going to learn more about thermodynamics and this fact of adding the grains of sand until the piston mass doubles actually is enough information to learn more about this and solve this problem. That tells you what type of process we use, and so that'll be maybe in the next chapter or later in this chapter, I forget which. So yeah, that's enough. We will learn how to do that, and the type of process will help us figure this out, in addition to the ideal gas law.